We're going to look at special right triangles and the Pythagorean theorem. Special right triangles you learned in geometry and the Pythagorean theorem is really a huge part of trigonometry. So the Pythagorean theorem that you learned in 9th grade or 10th grade geometry, whenever you took it, says the following. If we take the area of the square off of the one leg and add it to the area of the square off of the other leg of a right triangle, it'll equal the area of the square off of the hypotenuse. And we get this a squared plus b squared. It's the sum of those two areas added together gives you the area of the square off of the hypotenuse. You're going to see the Pythagorean theorem throughout this unit. I'd like you to be able to see the proof of the Pythagorean theorem.
We saw that if we have a right angle triangle like this, with sides A, B, and C, then the Pythagoras theorem says that c squared will equal a squared plus b squared. Let's move on to a new page to understand why. The process to understand the Pythagoras theorem is pretty similar to the one for a plus b the whole squared. We draw a line of any length and mark a point on it. This point can be marked anywhere on the line. We name the parts A and B. This length will be A plus B. Next, we complete the square with A plus B as its side. This is a square in which each length is A plus B. Now we try to make the same division on each segment. We mark points here, here, and here. The points should be marked such that this length is B, this length is A, this is B, this is A, and these two lengths are also equal to B and A. We can see that we have 4 points, one on each side. This time, we join the adjacent points. If you draw this on a piece of paper, you will notice that the figure formed inside is a square. Let the length of the sides be c centimeters. Look at the different parts that are formed. The outer square is made up of 5 parts. This square of side c centimeters in between and 4 right angle triangles with height A and base B. Let's zoom out a bit and try to find the area of the outer square. The area of the square can be calculated in 2 ways. The first way is side multiplied by side. It can be written as a plus b multiplied by a plus b, which equals a plus b the whole squared. And the area of the outer square also equals the sum of the areas of these 5 parts. The area of this square is c squared. Observe that each of these triangles will have the same area as their height and base is the same. Area of each triangle is half AB. To include the area of 4 triangles, we just multiply this with 4. Their total area would be 4 multiplied by half AB. 2 times 2 is 4, and we get the area of the outer square as c squared plus 2AB. Both these are the area of the outer square. Equating these two, we can write c squared plus 2ab equals a plus b the whole squared. And using the identity for a plus b the whole squared, we write this as c squared plus 2ab equals a squared plus 2ab plus b squared. And cancelling out 2ab from both the sides, we get c squared equal to a squared plus b squared. This is the Pythagoras theorem.
The Pythagorean theorem does not have to have squares off of the legs. In all reality, as long as it's a regular figure or a semicircle, the theory works. If you take the area of the square off of this, or area of the semicircle off of that leg, and the area of the semicircle off of that leg, and add those areas together, those areas will equal the same as the area of the semicircle off of the hypotenuse, as long as you have a regular figure. So these would have to be equilateral triangles. And if you take those areas and add them together, it will give you the area of the equilateral triangle off of the hypotenuse. Special right triangles, you learn those in geometry. There's the 45, 45, 90. It is an isosceles right triangle, and the leg lengths have to be the same. And the length off of the hypotenuse is the leg length times the square root of 2. The second one that you learned is the 30, 60, 90. Across from the 30-degree angle is the leg length x. The hypotenuse is always double the short leg length. And across from the 60-degree angle is the short leg length times the square root of 2.
So here is the 30, 60, 90 triangle. The 30, 60, 90 triangle is seen over and over again throughout many years of math, so it's definitely something worth memorizing. Note that since one of the angles is a 90-degree angle, this is indeed a right-angled triangle. Now across from the 30-degree angle is a length of 1. Across from the 60-degree angle is a length of square root of 3. And finally, the hypotenuse has a length of 2, which is across from the 90-degree angle. It's worth keeping in mind, however, that the 30, 60, 90 triangle side lengths that we memorize are just ratios. So that's 1 to square root of 3 to 2. For example, let's say we're given a triangle with a side length of 10 for the side that's opposite to the 30-degree angle. In this case, since that's 10 times more than the one on the 30, 60, 90 triangle, we should multiply all of the ratios by 10 as well in order to get the same triangle to scale. And there you have it. You know how to find the length of a triangle given just one of the lengths and the angles, since you'd know the proportions that each side would be. The next special triangle we will look at is the isosceles triangle, which consists of angles 45, 45, 90. This triangle will have side length proportions of 1 to 1 to square root of 2. So if we were given a triangle with these angles and were provided with just one side length of 4 centimeters across from the 45-degree angle, then the other leg would obviously be 4 centimeters in length. The hypotenuse would also be multiplied by 4, and if we wanted to show that in the entire radical form, then we would just square it and put it under the root sign, multiplying it by 2 to give us root 32. Great! So make sure you try to memorize these special triangles and their ratios for their side lengths, since these will be used over and over again in various concepts throughout mathematics. But that's it for this video, guys, and we will see you in the next lesson.
Let's do a couple application problems. The first one, if we know that this side is 30, this angle right over here has to be 60 degrees. And if the whole thing is 90, this would be a 30-degree angle. So we can begin by saying the length across from that 30-degree angle is 7. That requires then the hypotenuse to be 14. The hypotenuse with this triangle right here, because it's double that leg length. Now if I look at this next triangle, here I have this 30-degree angle, and across from the 30-degree angle we have 14. This would be the 60-degree angle, so that's 14 square roots of 3. We don't actually need that one, but the hypotenuse here would be 28. Now we have this bigger right triangle, and this right triangle right here is a 45, 45, 90. So if this leg length is 28, so is this one, and the hypotenuse is going to be 28 square roots of 2. Let's look at a next example. If I look at one angle there is 45, this also has to be 45. This would be a 30-degree angle. So across from the 30-degree angle, I have 4. So across from the 60-degree angle, it had to be 4 square roots of 3. The hypotenuse here would have to be 8. This other triangle, the 45, 45, 90, if we take the hypotenuse is equal to the leg times the square root of 2. So the hypotenuse is 8. The leg, I don't know that length, square roots of 2. And so I'm going to divide by the square root of 2 over the square root of 2. Of course, you can never leave a radical in the denominator. You know that. So this would be simplifying it. 4 square roots of 2 is equal to that leg length of y. And of course, if you take 4 square roots of 2 times the square root of 2, that's going to give you this right over here. All right, looking at some of the different values, again, this is 8 square roots of 2, has to be. It says that they are the same thing. And if we take the leg length times the square root of 2, so 8 square roots of 2 times the square root of 2, it's going to give us the hypotenuse. So that's 8 times 2, or 16 for this hypotenuse. If this is 16, across from the 30-degree angle right over here, if this is 60, of course, we know that this has got to be 30 degrees. This is going to be 8. So let's see, where are we at? And this will also be 16. We have this equilateral triangle that we're looking to find the height of. And if this is 60, this is my 30, this has got to be 8 square roots of 3. All right, 2 more just review type questions for you. They come from geometry. The next one has to do with the circle. You studied this in geometry. If it is equilateral, that means all of these angles right here are the same length, and the altitude right here, that's the height of the triangle, 90 degrees, is given to you as 36, and we need to find the area. Well, the area is 1/2 the base times the height, so it sure would be nice to know what the base would be when we're finding the area. Again, the altitude is 36. So how long is one of the sides? Well, if this is 60 and it's across from 36 is across from the 60-degree angle, remember the short leg times the square root of 3 is equal to the long leg. So I don't know the short leg, but if I multiply that by the square root of 3, you get the long leg, which is 36. So I'm going to divide by the square root of 3 and divide by the square root of 3, but you can't leave a radical in the denominator. So it looks like x is equal to 12 square roots of 3. That's just one of these, so the whole thing, if we multiply that by 2, would be 24 square roots of 3. So to find the area, it's 1/2 24 square roots of 3 times 36. 2 can go into 24 12 times. So in order to finish this problem out, you're just going to take 12 times 36. And when you get 432 square roots of 3. This last one, I know you remember doing these in geometry when you're finding the lateral area, the area of the base of the triangle, the total surface area, and the volume. So I'm going to start with the base of this triangle. Remember the formula for the base of this triangle, because it's equilateral, is 1/2 the hypothum times the number of sides you have times the length of each of your sides. That is the area of the base. And so if I look at this base figure, I have that the hypothum is given to me, or I can figure that out. I guess that's what my plan is. But I know this side is 30. This is a 60-degree angle right here. So half of this is going to be 15. So the hypothetical is going to be 15 square roots of 3. I can find the area of the base. Now the area is 1/2 the hypothetical, which is 15 square roots of 3 times 30 times 6. Multiplying that together, I have my area is 1,350 square roots of 3. If I wanted to find the lateral area, formula again from geometry, 1/2 the perimeter of the base times your